What's up, everybody? Welcome to Kenny Kinetics, where learning is made easy. Today, we're going to be taking a deeper look at what sensory information is processed by the spinothalamic tract. So let's go. Y'all, let's dive into this spinal tract. Alright, so to start, I got my girl in the kitchen cooking up some food. You know, she turned on the stove and she starts whipping the yes, whipping the flipping the what, whipping the flipping the A. Alright, so to start, you know, I got my homegirl in the kitchen and she cooking up some food. She turned the stove on and she started whipping the yes, whipping and flipping it what, whipping and flipping it. So after she's done and she turns on the stove, she moves the frying pan off of the stove. But then all of a sudden she get a phone call, brrr, and it's her homegirl. So she answered the phone like, "Hey girl, what's up?" She gets so into the conversation that she forgot that she already moved the frying pan off. So when she goes to move the frying pan, her hand touches the hot stove. She immediately pulls her hand away from the stove and she starts rubbing her hand as she feels some pain. And then after a couple of hours, that sharp pain turns to like a dull pain and her entire hand starts to throb. How is the brain able to sense this as painful? In order to understand this, we have to take a deeper look at our hand to see what's going on. So under the skin, you have mechanoreceptors that process touch, pressure, and vibration, as we saw in the dorsal column medial lemniscal tract, but you also have free nerve endings in the skin as well. There are numerous of free nerve endings within the body, but we are mainly going to focus on two types, A delta fibers and C fibers. A delta fibers detect fast discriminative pain, noxious mechanical stimulation, and noxious thermal stimulation, specifically extreme cold temperatures. Let's take a look at an A delta nerve fiber. Here we have the axon of the nerve, as well as the myelin sheath here surrounding the nerve. And between the myelin sheath here are the nodes of Ranvier. Myelin sheath helps increase the speed of the signal as it jumps from one node to another node on the nodes of Ranvier. A delta nerve fibers have a thicker diameter, which increases its conduction speed, and it also is covered with the myelin sheath, which again helps to increase its conduction speed. This is why we are able to process pain so quickly when we touch a hot stove, like in the example in the animation, or when we stub our toe on the side of the bed. A delta fibers have a quick conduction rate with its thick diameter and myelin sheath, which allows the signal to be processed in the brain quickly. Now let's take a look at C fibers. C fibers are responsible for slow, poorly localized pain, noxious mechanical pain, and noxious heat. C fibers have a small diameter and they are unmyelinated, which means that it takes a longer time for it to relay the signal to the brain. You can think of C fibers as the tortoise and A delta fibers as the hare. C fibers move extremely slow and A delta fibers move extremely quickly. C fibers are a part of the divergent pathway of the spinothalamic tract, and A delta fibers are a part of the conscious pathway of the spinothalamic tract. Here, we are going to start with A delta fibers in the conscious relay pathway. A delta fibers, again, are in charge of fast discriminative pain and extreme cold temperatures. Here we see an A delta nerve fiber in the hand. Notice its thick diameter and its myelination. Fast discriminative pain and extreme cold temperatures are picked up by the A delta fiber and travels to the back of the spinal cord through the dorsal root ganglion. Within the spinal cord in the gray matter, you have 10 different Rex lamina. Each of the 10 layers of Rex lamina and the gray matter of the spinal cord are responsible for receiving and transmitting different information. Rex lamina 1 is responsible for receiving and transmitting noxious stimuli. So extreme cold temperatures from A delta fibers synapse on Rex lamina 1. Rex lamina 2 is responsible for receiving and transmitting noxious stimuli, specifically pain. So fast discriminative pain from the A delta fiber gets relayed onto Rex lamina 2. Rex lamina 2 is also known as the substantia gelatinosa. Here, the A delta fibers synapse on Rex lamina 1 and Rex lamina 2. As they synapse on a Rex lamina, this is where the second order neuron is located. Once they synapse with the second order neuron within the Rex lamina, they decussate or cross over the middle of the midline and enter the anterior lateral pathway. It continues to ascend up through the medulla, the pons, and the midbrain until it reaches the cerebrum. If you remember from my last video, the signal travels to the VPL of the thalamus and synapses with the third order neuron. Here the signal gets relayed specifically to the area in the cerebrum where the hand is located. This is how the brain knows that there was some type of damage to the hand when touching the hot stove. Now let's recap the order in which the signal travels through the anterolateral or spinothalamic pathway from the conscious relay path. Number 1. Fast discriminative pain and extreme cold temperatures enter through the posterior aspect of the spinal cord through the dorsal root ganglion. This is known as the first order neuron. Number 2. The signal synapses with the second order neuron in Rex lamina 1 and Rex lamina 2, aka the substantia gelatinosa, in the gray matter of the spinal cord, travels through the anterior white commissure and decussates as it enters the spinothalamic tract. This is known as the second order neuron. Number 3. The signal continues to ascend through the spinothalamic tract within the medulla, the pons, and the midbrain until it reaches the VPL of the thalamus. Number 4. Here the signal synapses with the third order neuron in the VPL of the thalamus. This green right here is the third order neuron. Number 5. The signal is consciously processed in the cerebrum, aka the somatosensory cortex, and it relays the pain to the area where the hand is located. This is how we know exactly what area in our bodies we feel pain. After we feel pain in our hand from the hot stove or in our toe after we stub it on the side of the bed, why does the entire hand and the entire foot start to hurt hours later? Why do we always get so mad when we stub our toe? Let's take a look at the divergent pathway of the spinothalamic tract to understand this some more. C fibers are responsible for slow, poorly localized pain, noxious heat, and crude touch. Crude touch is the feeling of a touch in a broad area, so you can't really pinpoint where you're feeling the touch. Think of someone giving you a nice warm hug. Here we have a C fiber, and also notice the small diameter and the lack of myelin. Since the C fibers conduct at a slower rate, it is playing catch up with the pain that we feel. The C fiber enters the dorsal root ganglion at the back of the spinal cord and synapses with the second order neuron in Rex lamina 1 and Rex lamina 2, aka the substantia gelatinosa. It decussates or crosses over the middle of the spinal cord and passes through the spinothalamic pathway. The signal continues to ascend through the spinal cord until it gets to the reticular formation. The reticular formation is located throughout the medulla, pons, and midbrain, but I just have it depicted here in the pons. The reticular formation is responsible for arousal, attention, and the sleep-wake cycle. Ever wonder why sometimes you get awakened from your sleep because of pain? Well, this is why. The C fiber sends that pain information to the reticular formation, which can have an effect on your arousal, attention, and sleep. This is called the spinal-reticular tract. The signal continues to ascend until it reaches the midbrain. Within the midbrain, you have the periaqueductal gray and the superior colliculus. The periaqueductal gray is a part of the descending modulation of pain. It can send enkephalins, aka opioids, to an interneuron down in the spinal cord. Here, it can decrease the intensity of pain coming from the A delta and C fibers before it even enters the spinothalamic tract. If the intensity of the signal from the periphery is decreased before it even ascends up to the brain, then by the time it gets to the brain and is processed, it's going to be processed as less pain than what it would have been before if the periaqueductal gray didn't activate the descending modulation of pain tracts. The superior colliculus turns the eyes and head to the location of the stimulus. We are able to orient our eyes and head to the stimulus to make sure that we are not in danger. We will talk more about how this works through the tectospinal tract. The signal travels up to the periaqueductal gray and the superior colliculus in the midbrain. This is known as the spinal mesencephalic tract. Within the thalamus, other than the VPL of the thalamus, you have the intralaminar nuclei and the medial nuclei. Information that gets relayed to these nuclei are sent to the insula, the amygdala, the anterior cingulate cortex, and the dorsolateral prefrontal cortex, in which I do not have depicted on the screen. All of these areas play a role in the emotional aspect of pain. These areas collectively are known as the spinal emotional pathway. Now let's recap the divergent pathway of the spinothalamic tract. Number 1. Slowly localized pain, extreme heat, and crude touch into the posterior aspect of the spinal cord through the dorsal root ganglion. This is known as the first order neuron. Number 2. The signal synapses with the second order neuron in rex lamina 1 or rex lamina 2, aka the substantia gelatinosa. The signal then decussates or crosses over the middle of the spinal cord and enters the spinothalamic tract. This is known as the second order neuron. Number 3. The signal travels to the brainstem to the reticular formation. Here, the pain can interfere with your arousal, attention, and sleep-wake cycle. This is known as the spinal reticular tract. Number 4. The signal continues to travel in the spinothalamic tract until it reaches the midbrain. Here, the signal synapses with neurons in the periaqueductal gray and the superior colliculus. The periaqueductal gray can modulate pain through descending inhibitions, and the superior colliculus orients the head and eyes to where the stimulus is. Collectively, this is known as the spinal mesencephalic tract. Number 5. The signal gets sent to the intralaminar nuclei and the medial nuclei of the thalamus. The thalamus then relays the signal to the anterior cingulate cortex, the insula, the amygdala, and the dorsolateral prefrontal cortex. Collectively, this is known as the spinal emotional pathway. Alright everyone, we've covered a lot so far, but hopefully you guys are still with me. The last thing that I want to take a look at is the clinical significance of the spinothalamic tract. Why do we care so much about knowing all of this information? It all becomes important when we talk about spinal cord injury. So within the body, you have the central nervous system and the peripheral nervous system. The spinal cord syndrome that we are going to be looking at occurs when there's damage to the spinal cord and it gets split in half. This is known as Brown-Séquard syndrome. Some common causes are gunshot wounds, stabbings, motor vehicle accidents, vertebral disc herniation, and tumors. Here's a cross-section of the spinal cord with the spinothalamic tract. With Brown-Séquard syndrome, the spinal cord gets split in half. So this causes damage to this side of the spinal cord. Here, all the information from A delta and C fibers are coming into the spinal cord, but as it crosses over, it can't cross over because this side of the spinal cord is damaged. That means that the signal cannot ascend up into the brain and be processed here in the cerebrum, as well as the other parts of the divergent pathway. Since we know the information crosses over in the spinal cord and gets processed on the contralateral side, this means that the person will have loss of pain, extreme temperature, and crude touch on the opposite side since the information can no longer get processed. So since the signal's coming in from the left side, and typically it crosses over to the right side and gets processed on the right side of the brain, that can't happen anymore. So the person will have loss of pain, temperature, and crude touch on the opposite side of the body. In Brown-Séquard syndrome, the dorsal column medial lemniscal tract also gets affected. If you remember from my past videos on the dorsal column medial lemniscal pathway, it is responsible for light touch, vibration, and conscious proprioception. This information doesn't decussate until the level of the medulla. So in this case, the person will have loss of light touch, vibration, and conscious proprioception on the ipsilateral or same side. This is because in the dorsal column medial lemniscal tract, the sensory information ascends up on the same side and then it crosses over in the medulla. But since we see the damage is here in the spinal cord, that signal is on the same side, which means that you'll see these deficits, loss of touch, vibration, and conscious proprioception on the ipsilateral side. This is why knowing where these spinal tracts decussate are extremely important, so that you know what impairments your patient will have when you're treating them. Alright everyone, thank you so much for watching. Make sure you subscribe, like, share, and leave comments. Tune into my next video when I talk about the spinocerebellar tract. Thanks for watching.